Hello everyone, this is Rohan, and in this video I'm going to demonstrate how to find out the slopes and deflection in a simply supported beam using conjugate beam method. I hope all of you have seen my lecture number 1, that is Introduction to Conjugate Beam Method, because in this problem I'm going to be using a lot of references from that lecture. I am posting the link in the description below. So before you start with this lecture, first, please see the introduction lecture to conjugate beam method. Okay, having said that, let's quickly jump on to today's problem, that is find the slopes at A and C and deflections at B for the simply supported beam loaded as shown in figure below. Also, find the maximum deflection in the beam. So what we have with us today is a simply supported beam ABC having a hinge support at A and a roller support at C, and at the point B, which is at a distance 6 meter from A and 3 meter from B, you have a point load of 120 kilonewton. Moreover, the portion AB has a moment of inertia of I and the portion BC has a moment of inertia of 2I. So this is what we will call as the real beam. And the first step to solve any problem using conjugate beam method is to convert the real beam to the conjugate beam. Now the conjugate beam is going to be of the same length as the real beam, but the supports usually change. But since it is a end hinge support, this will remain as a end hinge support, and since this is a end roller support, it will remain as a end roller support. So as you can see here, ABC same length, A remaining the same as well as C remaining the same. This is the conjugate beam. This has already been discussed in the first video, that the conjugate beam of a simply supported beam remains as a simply supported beam. So now our next step is to find out the M by EI diagram of the real beam. Now, in order to do that, I will have to first find out the support reaction, either VA or VC. Alright, so in order to do that, I will be using the equation of equilibrium. Summation of MC is equals to 0, and I am going to take clockwise as positive. Now, what are the loads that I have to consider? The first one is VA and the other one is 120 kilonewton, and I have to consider the summation of the moment due to these two loads equals to 0. So let's see. So it will be VA multiplied by 9, that is 6 plus 3, 9, and it will, since it is in the clockwise direction, so it is positive, and minus 120 into 3 since it is anti-clockwise, so therefore it is minus, equals to 0. So that is the summation of MC equals to 0, and if I solve this, I get VA is equals to 40 kilonewton, and since 40 kilonewton is coming as positive, therefore my chosen direction of upward is correct. So VA is equals to 40 kilonewton. Now I really don't need the value of VC, so I'm not going to waste my time finding it out. If you want to find out, you can easily find it out by using summation of Fy is equals to 0. Anyway, so now I'm going to concentrate on finding out the M by EI diagram. Alright, so in order to find the M by EI diagram, of course the moment at A and the moment at C will be 0. That is already something we know, right? So I have to find out mainly the moment at B. But since B is at a point where just to the left the moment of inertia is I and just to the right the moment of inertia is 2I, therefore the value of M by EI will have two values at B. So if I consider just to the left and considering the value of I as I, so then I will have the moment at B due to 40 kilonewton as 40 multiplied by 6 divided by EI, and that is going to be 240 divided by EI. So I'm going to simply join this with a straight line and just see, this is left of the section clockwise, so this is positive. I'll write that later. And then again, if I consider just to the right where I have to take the value of I as 2I, then it will be what? The same thing, 40 into 6, but it will be divided by E into 2I. So it will be 120 divided by 2I. So I have a steep drop here. And again, as I told you in the beginning only, that at C it is 0. So I can just connect this by a straight line, and since everything is left of section clockwise, so therefore it is going to be positive in nature. So the M by EI diagram is positive in nature, having a peak 240 divided by EI coming down to 120 divided by EI. Alright, now in the next step, I'll have to bring back the conjugate beam, right? I have to bring back the conjugate beam and apply the M by EI diagram of the real beam that we have found in the previous slide as the loading. So this has to be now applied as a loading. Now as we knew, the M by EI diagram was positive, and according to the sign convention, if the M by EI diagram is positive, then the loading will be in the upward direction. So here you can see I have drawn the loading in the upward direction. For simplicity, I have divided the entire loading into two uniformly varying loads. One is uniformly varying load of a base 3 meter and height 120 divided by EI, and the other one is of base 6 meter and height 240 divided by EI. So this is the conjugate beam and this is the loading that is acting on it. Now before I can move on to find out the shear force and bending moment in the conjugate beam, I'll have to find out the support reactions RA and RC. In the lecture 2, where I had solved the cantilever beam, this step was skipped because I could easily go from the free end and keep on finding the moment without finding the support reaction. But here I have no choice but to find out the support reaction since none of the ends are free. Alright, now how will I find out the support reaction? Same way, I'll be using the equations of equilibrium. So summation of moment about C is equals to 0, clockwise positive. So I'm going to be finding the moment about this point. So therefore the three loads that I have to consider is this downward RA, this upward UVL of 240 divided by EI having a span 6 meter, and this upward UVL of 120 divided by EI having a span of 3 meters. So let's see one by one. Okay, so the first one is minus RA multiplied by 6 plus 3, that is 9, minus RA into 9, plus this is half into base, that half into base into height, that is half into 6 into 240 divided by EI, multiplied by, please see, the CG of this triangle. From B the distance is 1/3 of 6. Okay, but since I am finding out the moment about C, I'll have to add this 3 meter to it. So therefore here I have 1/3 of 6 plus 3. Okay, so the distance of the CG from RC is 1/3 of 6 plus 3. Lastly, considering this UVL, I have plus half into 3 into 120 divided by EI multiplied by the CG of this triangle is at a distance 2/3 of 3 from C, and that I will equate to 0. If you simplify this, you get somewhat like this. I have solved it and you can find out the value of RA is equals to 440 divided by EI. Now since this has come as positive, therefore my chosen direction of downwards is correct. So I'm going to be writing as RA is equals to 440 divided by EI. Alright, now in order to find out RC, I'll be applying another equation of equilibrium, summation of f of y is equals to 0, and I'm going to take upwards as positive. So the four loads that I have to consider is RA, RC, this UVL and this UVL. Alright, let's see. So it will be minus RA, right, plus half into 6 into 240 divided by EI plus half into 3 into 120 divided by EI and minus RC is equals to 0. So simply putting the value of RA as 440 divided by EI and simplifying it, I will get the value of RC as plus 460 divided by EI. And since the value of RC has come as positive, therefore my chosen direction of downwards is correct. So I will be writing directly here as 460 divided by EI. So what I have in front of me is the conjugate beam, the loading as well as the support reactions of the conjugate beam due to the loading. So I'm well equipped to start finding out the slopes and deflection in the real beam by finding out the shear force and bending moment in the conjugate beam. So let's see one by one. So here I have taken the screenshot of the same, which I'm going to be repeating for each and every slide from now. Okay, so what was the first thing that was asked? To find out the slope at A in the real beam, that is theta A. What is that in the conjugate beam? It is nothing but the shear force at A in the conjugate beam. Now, what is the sign convention for shear force? Left of section, downward force, positive. So here at A I have only one downward force, that is 440 divided by EI. Nothing else needs to be considered. So therefore directly I can write this as minus 440 divided by EI. And since this has come out to be minus, therefore as per the sign convention of conjugate beam method, the rotation at A will be clockwise. So in the final step I'll have to write this as 440 divided by EI radian in the clockwise direction. Now of course in this problem the value of E and I is not given, so all my final answers will have the term EI. Alright, in the previous problem of cantilever beam the value of EI was given, so I had put the values and found out the answer. Here it is not given, so simply I'll keep it as EI. So this is the first answer, that is slope at A in real beam is 440 divided by EI radian in the clockwise direction. Next we are asked slope at C in the real beam. Slope at C in the real beam, that is theta C. It will be nothing but shear force at C in the conjugate beam. Again, if you look at C properly, there is only one downward force of 460 divided by EI. But just see that when we consider this, I'll have to consider this as right of the section, isn't it? I have to consider the shear force of right of the section. Now, as far as the sign convention of shear force goes, right of section downward forces are taken as positive. So here directly I can write the shear force at C in conjugate beam will be plus 460 divided by EI. Okay, plus 460 divided by EI. And since this has come out to be plus, therefore the rotation is in the anti-clockwise direction. The slope at C is in the anti-clockwise direction. So another answer we had found out, that is slope at C in the real beam is 460 divided by EI in the clockwise direction. Similarly, if you were asked to find out the slope at any point, okay, maybe at B, it is not asked in this question. If you have to find it out at B, what do? You simply find out the shear force at B in the conjugate beam, or any other point. You have to simply find out the shear force. You have the loading, you have the support reactions, you can easily find out. Now let's move on to the third thing that has been asked, that is the deflection at B in the real beam. Deflection at B in the real beam is nothing but the bending moment at B in the conjugate beam. So I have to find out the bending moment at B. Bending moment at B I have to find out. I am going to find the bending moment from right. So the only two forces that I have to consider is this downward 460 divided by EI and only this triangular load of 120 divided by EI. Now let me remind you what is the sign convention for bending moment. Right of section, anti-clockwise moment is taken as positive and clockwise moment is taken as negative. All right, so keeping that in mind, let's see one by one the terms. So the first term will be minus 460 divided by EI into 3. 460 divided by EI into 3. Why? Because it is clockwise in direction. It is clockwise in direction. Now, the next term will be plus half into 3 into 120 divided by EI and then multiplied by the CG, that is 1/3 of 3. Okay, so if I simplify this, I will get the answer as minus 1200 divided by EI. And since this is bending moment has come out to be negative, that means the deflection is in the downward direction. This is as per the sign convention of conjugate beam method. You can find it in my lecture 1. Okay, so the deflection at B is 1200 divided by EI meter in the downward direction. Now something interesting. Now we have been asked to find out the maximum deflection in the real beam. Maximum reflection in the real beam, that means Y max. Do we know where the maximum deflection will be? We don't know. We don't know. So, but we know one thing, that since deflection in the real beam is equals to bending moment in conjugate beam, therefore maximum deflection in real beam will be maximum bending moment in the conjugate beam. And where does maximum bending moment occur? Maximum bending moment occurs where the shear force is zero. So maximum bending moment in conjugate beam occurs where the shear force is zero. So if we can find out in the conjugate beam where shear force is zero, then we can easily find out the maximum deflection in the real beam. So let us assume that the shear force is zero at a section xx dash at a distance x from A. Please see this diagram. Xx dash, this is where the shear force we are assuming it to be zero, and it is at a distance x from A. Distance x from A. All right. Now, in order to go further, I will need to know the value of the intensity of the UVL at a distance x, right? Here it is 240 divided by EI, but what is the value of the UVL here? So let's find that out by unitary method. So for 6 meters, the intensity is 240 divided by EI. For 6 meters, the intensity of UVL is 240 divided by EI. So therefore, for 1 meter, how much will it be? It will be 240 divided by EI divided by 6. That is 40 divided by EI, right? This is simple mathematics. So therefore, for x meters, the intensity of the UVL will be 40 divided by EI into x. So 40x by EI, right? So at the distance x, the value of the UVL is 40x by EI. 40x divided by EI. Now, let me write a general equation of shear force at this point. Okay, what are the two things that I have to take into account? One is this RA, that is in the downward direction, and one is this upward UVL, having the base as x and the height as 40x by EI. Left of section upwards force is taken as positive. Okay, so therefore shear force at x will be minus 440 divided by EI, because it is downward, and plus, since this is upward, half into x into 40x by EI. This is the shear force at x. And what is the shear force at x that we have assumed? We have assumed it to be 0. And if I simplify this, I'll get it in this format, and if I solve it in my calculator, I get the value of x is 4.69. The value of x is 4.69. So that means at this distance, at a distance 4.69, the value of shear force in conjugate beam is 0. That means the value of bending moment is maximum in the conjugate beam at a distance 4.69 from A, and that means in the real beam at a distance 4.69 meter, the deflection is maximum. So now all I have to do is to find out the bending moment at 4.69 meter from A. Okay, so maximum deflection in real beam Y max is equals to maximum bending moment in the conjugate beam, that is bending moment at 4.69 meter from A. Alright, so I have to find out the bending moment at this point, 4.69 meter far away from A. So again, two things has to be considered. One is the RA and the other one is this UVL, having a base 4.69 and a height 40x by EI, where x is equals to 4.69. Let's see. So here I'll have a hogging moment of minus 440 divided by EI multiplied by 4.69. Okay, 440 divided by EI, and this distance is 4.69. And then I'll have a sagging moment of half into base, that is 4.69, and height is 40x by EI, but here I have put the value of x as 4.69. Okay, so half into base into height and multiplied by the CG. The CG will be at a distance 1/3 of 4.69. So if you simplify this, you will get the answer as minus 1375.86 divided by EI, and since it is coming as minus, therefore the deflection at this point X is going to be in the downward direction. Please remember at B we had got the value of 1200, and here you can see a bigger value. That means chances are that our answer is correct, that this is Y max, that is 1375.86 divided by EI meter in the downward direction. Now let us bring back the real beam here. Now due to this we have, again I will like to add another point here because this is important to us, that is D, that was 4.69, because here the bending moment was the deflection was maximum. So these are the values that we had got: theta A, theta C, YB and YD. So let us see this with the help of a deflected shape. So this is the original shape of the beam. I've drawn it in dotted lines because after the loading it will become something like this. Okay, and the naming here is something like this, where A and C remains in their position. There is no downward deflection, but there are slopes, and D comes down to D dash and B comes down to B dash. Now let's see. At A, the slope here is nothing but theta A. Okay, this theta A, and as you can see, to come from its original position to its deflected shape, it has to come in the clockwise direction, which matches with our answer, that it is in the clockwise direction. Similarly for C, here to come from its original position to the deflected shape, it has to come in the anti-clockwise direction, which is again matching with our answer. And obviously this distance B to B dash is nothing but YB, which is in the downward direction, again matching with our answer, and D to D dash here is the Y max, which is again in the downward direction, matching with our answer. So with the help of this, I hope I have successfully demonstrated to you how to find out the slopes and deflections in a simply supported beam using conjugate beam method. If you have any questions, you can write in the comments below. Thank you for your attention.